Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 7, the mean as a balance point. Classwork. In lesson 3, Robert gave us an informal interpretation of the center of a data set. In lesson 6, Michelle developed a more formal interpretation of center as a fair share mean, a value that every person in the data set would have if they all had the same value. In this lesson, Sabina will show us how to interpret the mean as a balance point. Example 1, the mean as a balance point. Sabina wants to show how long it takes students to get to school. She asks 2 students how long it takes them to get to school. It takes one student 1 minute and the other student 11 minutes. Sabina represents these data values on a ruler, putting a penny at 1 inch and another at 11 inches. Sabina thinks that there might be a connection between the mean of 2 data points and where they balance on a ruler. She thinks the mean may be the balancing point. Sabina shows her data using a dot plot. Okay, so the dot plot of number of minutes 1 through 12. And the reason they went to 12 was because it's a ruler and it's 12 inches, 1 foot. Sabina decides to move the penny at 1 inch to 4 inches and the other penny from 11 to 8 inches on the ruler. Noting that the movement for the 2 pennies is the same distance but in opposite directions. Sabina thinks that if 2 data points move the same distance but in opposite directions, the balancing point on the ruler does not change. Do you agree with Sabina? Okay, so here's the deal. She moved the coin from 1 to 4. Well, that is 1, 2, 3 inches to the right. She took the other coin that was at 11 and moved it 1, 2, 3 to the left to 8. All right. So if it was balanced when they were at 11 and 1, and you moved them both 1, it'd still be balanced. Move them both 2, it would still be balanced. Move them both 3, it would still be balanced. Okay. So I agree with Sabina. Now Sabina continues by moving the penny at 4 inches to 6. So then let's go 2 more to 6. To keep the ruler balanced at 6 inches, how far should Sabina move the penny from 8 inches and in what direction? Well, if we went 2 more, then this one has to go the opposite direction, which is left because the other one went right. And there we have it. So to keep it balanced, how far should Sabina move the penny from 8 inches? Okay, she should move it 2 more inches to the left. Okay. Okay, page 2 brings us to exercise 1 and 2. And it says, now it's your turn to try balancing 2 pennies on a ruler. Take 1 penny at 2.5 inches on your ruler. So what I've done is I brought in a ruler that is 12 inches long. And I am going to simulate a coin. So I will draw a circle that would be about the size of a coin. And let's see. Okay, so here's 2 coins I made. They're copper, they move around. Okay, so she is going to take 1 penny at 2 1/2 inches, which would be right there at 2 1/2 inches on the ruler. Where should the second penny be taped so that the ruler will balance at the center 6 inches? So if we were at 12 and 0, it'd be balanced. 11 and 1, 10 and 2, 2 1/2, 9 1/2. And there we are. So if we move this one 2 1/2 inches to the right, this one had to be moved 2 1/2 inches to the left. Okay, so the penny should be at 9.5 inches. Now what B says, how far is the penny at 2.5 inches from 6 inches? So the penny that is at 2.5 inches, they're asking how far it is from 6 inches. So what we would do is just count over. Okay, this is a half right here. And then we're going to go 1, 2, 3, and then this half. So it is 3.5 inches from 6 inches. Okay, so each penny actually is 3.5 inches from the 6 inches. And then part C says, is 6 inches the mean of the two locations of the penny, and explain how you know this. So if I move this another half inch to 3, then I move this to another half inch to 9. Now we're on even integers. And if I move this one 1 to the right to 4, and I move this one 1 to the left to 8, it's still balanced. Move this to the right to 5, move this to the left to 7, move this to the right to 6, move this to the left to 6, and we are now both at 6. So the answer to this question is yes. Okay, so yes, the mean of the two locations of the pennies is 6 inches. The distance of the penny that is below 6 inches is equal to the distance to the penny that is above 6 inches. All right, so number 2 says, move the penny that is 2.5 inches to the right 2 inches. So if I am right here at 2.5 inches, and this one is back at 9.5, like up here, and it says move the penny that is at 2.5 inches to the right 2 inches. There's 1, there's 2, now it's at 4.5. Okay, so the penny will be placed at 4.5 inches. B says, what do you have to do with the other data point, the other penny, to keep that balance point at 6 inches? So now we're off, and since we move this one 2.5 inches, we have to move this one to the left a half, 1, 2 to 7. Is that right? Oh no, they moved this one 2 inches. So we go from 9.5 to 7.5. So the answer to this is we would have to move the penny on the right 2 inches to the left. Okay, so there it is. Part C, what is the mean of the two new data points? Okay, so the mean is 6. It is the same value as the balance point of the ruler. Remember that the ruler might not balance at exactly 6 depending on the accuracy of the placement of the two pennies on the ruler. All right, page 3 brings us to example 2, balancing more than 2 points. Sabina wants to know what happens if there are more than 2 data points. Suppose there are 3 students. One student lives 2 minutes from school. Another student lives 9 minutes from school. So they have a penny here for the 2 minutes, and they have a penny over here for the 9 minutes. If the mean time for all 3 students is 6 minutes, she wonders how long it takes the third student to get to school. Using what you know about the distances from the mean, where should the third penny be placed in order for the mean to be 6 inches? Label the diagram and explain your reasoning. Okay, so here's the diagram. The penny on the left was at 2, and it was 4 inches from 6. The penny on the right was at 9, which is only 3 inches from 6. So in order for them to all average out to 6, then this other penny had to be at 7, which is 1 inch from 6. So the one penny was 1 inch, the penny at 9 inches was 3 inches from 6. So 1 plus 3 is 4, and that equals the other 4. So the third penny should be placed at 7 inches. The 7 is 1 inch from the 6 inches, and the 9 is 3 inches from the 6 inches. Combined, the total distance for the 2 pennies is 4 inches. Since the distance of the point on the left of 6 inches is also 4 inches, the mean is now 6 inches. Exercise 3 through 6 means you try it yourself, pause the video, see if you can do it. When you're done, unpause the video, and I will give you the solutions and see how you did. Okay, so here we go. Imagine you are balancing pennies on a ruler. Suppose you place 1 penny each at 3 inches, 7 inches, and 8 inches on your ruler. Sketch a picture of the ruler. At what value do you think the ruler will balance mark the balance point with the symbol, and it looks like a little triangle or delta. Okay, so here would be the sketch. Students should represent the pennies at 3 inches, 7 inches, and 8 inches on the ruler with a balancing point at the 6. So that's what your diagram should look like. And I think that's what I had up here where I showed the arrows and the numbers. Part B says, what is the mean of 3 inches, 7 inches, and 8 inches? Does your ruler balance at the mean? Okay, the mean is 6 inches, and yes, it balances at the mean. So if you tried this, it would balance. All right, page 4, part C. Show the information from part A on a dot plot. Mark the balance point with the symbol that. All right, so what they're saying is, go back to part A, this right here, they want it as a dot plot. So it should look like this. Okay, so we have a point at 3, a point at 7, a point at 8, and a balance point at 6. D, what are the distances on each side of the balance point? How does this prove the mean is 6? Okay, this is kind of a lengthy answer. The distance to the left of the mean, the distance between 3 and 6 is 3. One of the distances to the right of the mean is the distance between 7 and 6, which is 1. And the other one is the distance between 8 and 6, which is 2. The total of the distances to the right of the mean, 2 plus 1, equals 3. The mean is 6 because the total of the distances on either side of 6 is 3. Okay. All right, number 4 is, now suppose you place a penny each at 7 inches and 9 inches on your ruler. A, draw a dot plot representing these 2 pennies. Okay, so there's the dot plot. One at 7, one at 9. And then part B says, I already brought this in, the balance point at 6. Part B says to estimate where to place a third penny on your ruler so that the ruler balances at 6. All right, so what we're going to do here is, this is a distance of 1. And this is a distance of 1, 2, 3. So that means I would have to be moving something 1, 2, 3, 4. So it appears to me that the third penny should be placed at the 2-inch mark. Okay, so there's the reason why. 4 equals 3 plus 1. All right, so now it says part C, explain why your answer in part B is true by calculating the distances of the points from 6. Are the totals of the distances on either side of the mean equal? Okay, so the distance to the left of the mean, the distance between 2 and 6 is 4. One of the distances to the right, the one between 6 and 7, is 1. And the other one is between 6 and 9, which is a distance of 3. The total on the right, 3 plus 1, equals the amount on the right or left, which is 4. So the mean is 6 because the total distances on either side of 6 is 4. All right, page 5, number 5. Is the concept of the mean as the balance point true if you put multiple pennies on a single location of the ruler? I think we've already done this, right? So the answer is yes, the balancing process is applicable to stacking pennies or having more than one data point at the same location on a dot plot. Okay, remember we did the fair share interpretation with pets back a couple of lessons ago. Number 6, suppose you place 2 pennies at 7 inches and 1 penny at 9 inches on your ruler. Draw a dot plot representing these 3 pennies. Okay, so I'm just going to do it this way. So the first thing we're going to do is we're going to put a dot at 7 inches, which is right here. And there are 2 of them at 7, so that would be 2 dots here. And 1 penny at 9. So that'd be right there. So that's part A. Part B says to estimate where to place a 4th penny on your ruler so that the ruler balances at 6, and mark the point on the dot plot above. Mark the balance point with the symbol triangle. All right, so here's what I'm going to do. We want to balance at 6. So I'm going to put that symbol right here at 6. All right, actually it's off a little bit. How about right there? And then what I'm going to do is say, well, this coin here is a distance of 1 from 6. And this coin here is a distance of 1 from 6. And this coin right here is a distance of 1, 2, 3 from 6. These three on the right-hand side are a distance of 1 plus 3, which equals 5. Okay. So since it's a distance of 5, I would then need to move a penny from the center. It'd have to be 5 from the center, I mean, and that would be way down here at 1. So this is 1, 2, 3, 4, 5 away from 6 on the other side. So it says, explain why your answer in part B is true by calculating the distance of the points from 6. Are the total of the distances on either side of the mean equal? And the answer is yes, because 3 plus 1 equals 5, and this is 5. So the total of the distances to the left of the mean is 5. The total of the distances to the right of the mean can be found by calculating the distance between 7 and 6 twice. And since there are 2 data points at 7, then adding it to the distance between 9 and 6. Therefore, the total of the distances to the right of the mean is 5, because 1 plus 3 equals 5, which is equal to the total of the distances to the left of the mean. Okay, so example 3 says, finding the mean. What if the data on the dot plot were 1, 3, and 8? Will the data balance at 6? If not, what is the balance point and why? So the first thing I'm going to do is put a balance point at 6 and see if that's going to be true. And 8 is the only coin on the right of 6, and it is a distance of 2. The other side is 1, 2, 3. So already it's not equal, because this is a distance of 3 and this is a distance of 5. So we have a total of 8, and this is only 2. 8 does not equal 2. So in order for this to balance, if I move this 1 to the right, left, 1 to the left, okay, then I'm going to redraw these. And now it's going to be a distance of 2. And this is a distance of 4. And that totals 6. But this one is no longer 2. This one is a distance of 1, 2, 3. So there's 3. Well, 4 plus 2 is 6, and that doesn't equal 3. So that didn't work. So I'm going to move it one more. Try this one. So now I'm going to balance it at 4. Get rid of these, redraw it. Now this is a distance of 1. This is a distance of 3. That totals 4. And this is 1. Oops, forgot to change color. This is a distance of 1, 2, 3, 4. So there it is. 3 plus 1 equals 4. Okay. So what if the data on the dot plot were 1, 3, and 8? Will the data balance be at 6? The answer was no. If not, what is the balance point? The balance point is 4. And the reason is because of the sums of the distances. All right, so the data do not balance at 6. The balance point must be 4 in order for the total of the distances on either side of the mean to be equal. Okay, page 6, exercise 7 says, use what you have learned about the mean to answer the following questions. Recall from lesson 6 that Michelle asked 10 of her classmates for the number of hours they usually sleep when there is school the next day. Their responses in hours were 8, 10, 8, 8, 11, 11, 9, 8, 10, 7. It's hard to balance 10 pennies. Instead of actually using pennies in a ruler, draw a dot plot that represents this data set. Okay, so what I'm going to do is, here's an 8, put a dot there. A 10, that goes here. Another 8 goes here. A third 8, an 11, another 11, a 9, another 8, another 10, and a 7. Okay, there it is. That is number 7. B says use your dot plot to find the balance point. Okay. So what I'm going to do is I'm going to look at this. I'm going to say, well, let's see. How about putting it at 9? So 9 is already right there. So this is a distance of 1, and this is a distance of 1. And these are both distances of 2. So that's 1 plus 1 plus 2 plus 2, which equals 6. This is 1. Let me change colors. Oh, I didn't want to do that. I wanted to do that. Okay, so this is a distance of 1. This is also a distance of 1, and so is this, and so is this. So that's 1 plus 1 plus 1 plus 1. And then this one here is a distance of 2 plus 2. So 1, 2, 3, 4, 5, 6. And there you have it. Okay, so I was just approximating, and I started with this because it made sense to me, but it actually turned out to be the correct balance point of 9. Okay, so putting this into words, a balance point of 9 would mean the total of the distance to the left of 9 is 6, because 2 plus 1 plus 1 plus 1 plus 1 equals 6. And the total distances to the right of 9 is 6, because 1 plus 1 plus 2 plus 2 equals 6. Since the totals of the distances on each side of the mean are equal, 9 is the balance point. The data point that is directly on 9 has a distance of 0, which does not change the total of the distances to the right or to the left of the mean.